Welcome back. Now we'll look at paper 32, also of May-June 2024. And as always, the mark scheme for this paper has already been released. So as well as watching this video, I will also recommend checking the mark scheme. And of course, if the video is too slow, then you can watch at 1.25 or 1.5 times the speed. Okay, question 1 says, describe the effect of changing the allocation of bits used for the mantissa and for the exponent in a floating point number with a fixed total number of bits. Right, I mean, so like, yeah, okay, well, let's say, I mean, maybe this is confusing. So first we can just think, well, what's going to happen in denary? Now, let's say for the mantissa, this can be, let's say, what, 1.23. Now, of course, I mean, here we're going to have, what, let's say, 2 decimal places worth of precision. Now, if we use more bits, or in this case, well, more digits, of course, well, we can just increase the accuracy, right? Or we can increase the precision. So that's going to be the effect of let's say using more bits for the mantissa. Right, we're going to get more accurate or more precise numbers. Right now, if we think about the exponent, so of course in denary, well, it's going to be times 10 to the power or something. Now let's imagine we only have one digit for the exponent, so of course we can go well, let's say from -9, and well, let's say 2, 9. Now of course in binary, right, in 2's complement it's going to be slightly different. But of course, well, let's say for example, if we then increase the number of digits, and let's say we can go from I don't know, say -999, right, to positive 999. Well, of course, by increasing the number of digits, right, or in binary, well, it's going to be the number of bits. Then of course, what we're doing is we're increasing the range that we can represent. So both, let's say the smallest number and of course the biggest number as well. So yeah, let's just write that. We'll say what, using more bits for the mantissa. And we can say what this will allow us to let's say maybe allows us, right, to more accurately or more precisely represent numbers. Let's say what represent, I don't know, maybe numbers more precisely. I think that should be fine. Or, okay, all right, let's say, to a higher degree of precision. I think that's probably the best way to say it. Right, and then, let's say then we're increasing the exponent. Right, so increasing the exponent will basically increase the range of numbers that we can represent. Right, increasing the number of bits for the exponent. Let's see what will increase the range of values that we can represent. And I think for 2 marks, I mean, that should be okay. Increase, the range of values, right, that we can represent. Because of course, well, it's going to be 1 mark for saying what's the effect for on the mantissa. And obviously 1 mark for the effect on the exponent. Represent. Right, then it says real numbers are stored in a computer using floating point representation. Right, with 12 bits for the mantissa, 4 bits for the exponent, and 2's complement form for both the mantissa and exponent. Right, we want to calculate the normal floating point representation of positive, right, 54 point, right, in this system. Okay, then, so, well, first what we need to do, we need to calculate the fixed point representation. So I'm just going to think, well, let's go here, and I mean, probably we only need to go up to 64. I mean, right, maybe we need 128. Although, actually, well, in this case, right, we only need 64. Because, well, of course, what we would do is if we have bits left over, well, then we would add those bits on, on the right, okay, to make it more precise. Like, we're not going to add leading zeros at the start, because, well, if we have leading zeros at the start, then, well, of course, it's not going to be normalized. Right, so of course, well, here then there's going to be no 64s. Let's also go, 32, right, 16, 8, 4, 2, 1. And then obviously this is where it's going to get a little bit more difficult. Well, so 0.5, that's fine. Right, 0.25. Then I think if we have that, it's going to be 0.125. The next one is 0.0625. I think if we keep going, the next one I think is going to be 0.3125. And I think this is probably as kind of I guess let's say as small as they've halved it. Although maybe it's good to sort of know if you just halve it one more, right? What kind of what like half of that is going to be as well. But anyway, let's try and do this then. So 54, right, we want 32, right, then we want 16, that gives us 48. We don't want an 8. Right, then if we go 4, well, that gives us 52. Yeah, right, then if we go 2, okay, so here then there won't be a 1. Right, then to get the sort of 8, 1, 2, 5, well, of course, that's going to be a 0.5. Right, then if we go 0.25, well, that gets us to 0.75. Then if we have, well, 0.75 plus 0.125, well, I mean, that's going to be too big. But then, right, if we have 0.75 plus 0.625, then, yeah, I think this is going to equal, right, this, 8.125. So what I'm going to do now, I'm just going to draw the dot here. In fact, okay, hang on. All right, sorry. Yeah, so I'm going to draw the, well, okay, let's say the binary point here. But of course, what we want to do, well, we just want to move it. So if we count, well, 1, all right, 2, yeah, 3, 4, 5, and 6. So we then want to move that binary point 6 places to the left. And because we want to move it 6 places to the left, well, then that means we need to make the exponent positive 6. Because what we're saying is basically, I mean, I'm not going to, okay, yeah, well, yeah, okay, all right, maybe I will. So I'm going to write out the whole thing. We're saying that, right, this one here, right, so, well, this one, right, times 2 to the power of 6, because, well, yeah, that's what we're saying. Right, that's going to be equal to, and, well, okay, I mean, like, basically it's going to be equal to, this one we've calculated here. And if we think about that, I mean, that's why it has to be a positive 6, because, of course, if we think about this, well, this is what, positive 54, right? Therefore, if we have this, well, this is sort of, well, 0.5, right? 0.75, right? Obviously more. Right, this is, of course, going to be a small number, right? Therefore, we need to multiply it by a big number, right, to get back to our 54. I think a common mistake people make is, for example, they would think, well, if we're moving the binary point left, they would make that minus 6. But of course, well, 2 to the power of minus 6, this is going to be a small number. So if we have, well, a small number multiplied by another small number, of course, well, obviously, yeah, okay, the number is going to get even smaller. So let's just try and write down our answer, and hopefully that's made sense. So we want to go, what, 0, 1, 1. Yeah, I'm just, well, hopefully copying this down correctly. Yeah, I think, right, did I make a mistake there? No, maybe not. Alright, so let's add that extra 0. Right, then if we want 6, well, of course that's going to be 0. Right, then there's a 4. Yeah, then there's a 2. Right, then there's a 0. And yeah, let me just check this. Yeah, so I think that's fine. And of course, I mean, well, this would be where our dot would be. Although, yeah, of course, well, we don't need to actually include that right in the answer. Then we want to outline why protocols are essential for communication between computers. So I think here, let's say maybe provides, and we can say, okay, let's say provides a platform or operating system independent set of rules, maybe allowing successful communication to take place, right, between devices or between computers. Yeah, so I think something like that. Or let's say, yeah, provides a platform, right, / operating system independent. Because, I mean, I don't know, well, let's say we have a protocol, TCP, IP, UDP, or HTTP. Of course, these protocols should be able to be implemented on, well, let's say whatever platform, whatever operating system. Actually, well, let's also say hardware. I suppose really, I mean, platform is kind of, synonymous for operating system, really. But anyway, right, provides a platform operating system hardware, right, let's say independent. And I suppose rather than set of rules, we could say, well, standard, right, let's say, yes, standard. I'm going to say, right, standard, right, / yeah, set of rules. Right, yeah, maybe for sort of successful communication to be established and take place. Yeah, let's say maybe for, right, let's say successful, maybe connections to be established. Right, and communication to take place. Yeah, okay, right, communication to take place. And obviously, I mean, well, you can think, why does it have to be standardized? Now, let's just look at IP, for example. Now, IP, hopefully we know that, let's say in the header, and yeah, right, to be honest, yeah, I probably should have made that bigger. Right, so let's say here in the header, what we've got well, I mean, yeah, I guess more than 4 things. But I mean, one thing what's going to be the source IP, right? Let's call it SIP. Right, then what the destination IP. There's also going to be what the packet number, or yeah, also called the sequence number. Right, I mean, there's going to be things like the length, right? So let's say the amount of bytes. Now, of course, I mean, what's going to have to happen is we want to say, well, let's say the source IP should be, well, let's say 32 bits. All right, if we're talking about IP version 4. Of course, right, destination IP, again, 32 bits. The packet number, I don't know, maybe 64 bits. Yeah, the length, again, or maybe, I don't know, 32 bits. Now, of course, I mean, basically what anyone that's sending data, of course, has to send data, in that correct format. Like if, for example, I don't know, maybe they put the length first, and then they put, the source IP here, the packet number here. And of course, well, now the data is all in the wrong order, right? Maybe they've used, different size integers. So of course, well, the person that's receiving this, I mean, well, either they're going to interpret the data, but it's going to be the data in the wrong order. So it's just yeah, it's going to sort of provide problems basically. All the data is in completely the wrong format, and well, it's just not going to be able to be passed because let's say the data is too short, too long, or yeah, some other problem. All right, so that's why it has to be standardized. Right, then state the names of 2 different protocols associated with the sending and receiving of emails between computers. So actually, well, for sending there's only one, I think, what, SMTP. And if I remember correctly, I think maybe it's going to be send message. Yeah, like maybe this is correct, maybe it's wrong, but I think maybe send message. Let's say maybe transfer or transport. Yeah, I don't know, maybe transfer, or let's say protocol. I mean, yeah, like possibly that's slightly wrong, but I mean, I think it's kind of the general idea, right? Maybe transfer, maybe transport. Right, and then well, receiving. I mean, let's go for IMAP, right? Since this is the more modern one. So I think IMAP maybe like maybe internet, yeah, internet messaging or application protocol. And of course, I mean, well, here we only need 2, but you could also mention POP3. POP3, what, the post office protocol. Now POP3, this is older. So the difference between IMAP and POP3, well, IMAP, when you receive an email, or okay, well, all right, I mean, let's say not you, right, when your email server, so I don't know, maybe that's Gmail or Outlook, or yeah, like Proton Mail, right, whatever. I mean, when your email server receives an email, I mean, basically it's just going to store on the server. And then, for example, well, you can, connect to that email server, I don't know, from your mobile phone client or from your computer. And I mean, those emails are going to be downloaded then to the different devices. Right, let's say, yeah, this one is the mobile phone, this is maybe your laptop. And here, well, the emails are still stored on the server. And for example, even, I don't know, well, let's say you get a new mobile phone, or you like delete the email app from your phone. Well, if you then, let's say, got a new mobile phone and you try to access that email again, well, yeah, of course, right, in this case, you will be able to, because the email is permanently stored on the server. So, I mean, this is basically just modern email, right? I mean, this is what people are used to. Now, in contrast, POP3, well, POP3, this was the old style where, let's say, when you've downloaded the email, well, the email will then be deleted from the server. So in that case, you would get weird situations where, let's say, for example, I don't know, maybe you sort of first viewed the email on your laptop. Well, then if you try to log into your email on your, say, mobile phone, well, of course, I mean, you're not going to actually receive this email because, I mean, well, when you've downloaded it onto your laptop, well, then the email has actually been deleted from the server. And yeah, of course, well, that's why POP3 is actually not used that much, right, these days. Right, then we want to explain the meaning of the phrase BitTorrent protocol provides peer-to-peer file sharing. Okay, so probably we can say there's going to be many nodes in the network. It's going to be decentralized, so there's not a central server. And we can say, well, each node, well, okay, I mean, let's not say node, right? We can say each peer. Each peer can both seed and leech. So seed, well, I mean, basically this just means sending files. Leeching, well, that's going to be, let's say, downloading or receiving files. Yeah, okay, so I think we can probably say that. So let's say, yeah, maybe a network. Right, a network, right, consisting of many, well, let's say users, devices, right, let's say, or maybe nodes. Right, users, yeah, devices, right, nodes. And we can say what, without a centralized server. Yeah, no, I suppose actually in bracket, well, let's put right decentralized, since I think decentralized is also a kind of keyword they often look for. Right, so a network consisting of users, devices, nodes, I guess we can say peers, right, since I mean, yeah, that's really what they are. Right, peers without a centralized server. Yeah, we can say each peer has an equal status in the network. Right, yeah, has an equal status in the network. So it's not like where, let's say, a server would be sort of, more important than like a client. Yeah, I mean here, I guess they're all just kind of equal. Right, let's see, equal status in the network. Right, and we can say and can both, well, let's say seed, right, send files, and leech, right, or download, yeah, receive files. Yeah, and yeah, okay, right, can both. Right, let's say seed, and then in brackets we'll just put send files. Right, let's say yeah, and leech. So that's going to be receive or download files. And we can say maybe to, right, slash from, and let's say other peers. Yeah, I'm trying to think. I mean, what else can I add? Maybe just to fill up this space. So you could mention, for example, that you can download files from multiple people at the same time, right? Also, of course, you don't have to download the whole file from each person. Yeah, of course, the file. The file is going to be broken up into blocks, basically. So yeah, let's maybe say that. Right, let's say yeah, the files. Right, will be broken into blocks. I mean, yeah. Hang on. Okay, all right, hang on. Okay, let's say broken up. Yeah, broken up into blocks, or maybe yeah. I mean, I think blocks is okay. Right, and can be downloaded. Or okay, well, let's say right, yeah, and different. Let's say different blocks. Right, can be downloaded. Or I guess we could say can be seeded, right, slash leeched. And let's say yeah, to, right, from, yeah, different peers, simultaneously. Okay, and then, I mean, I think if you wanted to expand that, of course, you could mention, well, therefore this can make the network more resilient because, multiple people have copies of the file. Also, you can say, well, of course, the speed can, possibly increase because, you're downloading, right, from multiple people at the same time. But yeah, I think here we don't really need to talk about the advantages. We're just kind of explaining how it works, or yeah, kind of, yeah, I guess kind of like explaining the overall concept. Now we want to explain what is meant by the term non-composite data type and give an example of a non-composite data type. Now for this one, I will admit, doing paper one, I did see the definition they gave there because, well, I mean, basically they had this sort of, similar, but I think actually opposite question. They were actually asking for composite. So I think when we say non-composite, well, I think what they said is it doesn't have to be defined in terms of other data types. So if, for example, well, let's think about composite instead. Let's say you have, I don't know, like a record. Well, a record is going to be composed of other data types, right? For example, an integer, a Boolean, right, a real. Whereas, yeah, if it's non-composite, well, let's just say this. Maybe, yeah, is, or, yeah, I guess what isn't, right? Like, yeah, let's say isn't defined. Okay, right, isn't defined, right, in terms of other data types. And I suppose, well, let's say another word for that, right, basically means it's primitive. Yeah, let's say, right, i.e., right, yeah, i.e., right, it is a primitive data type. Or yeah, maybe, right, right, let's say, yeah, it can be primitive. I think, right, let's also say it's atomic. So atomic means it can only have one value. Whereas if we have, well, let's say, for example, yeah, I guess a record, right, or a set. Well, a record or a set, of course, they can hold multiple values. Yeah, or it also has to be atomic. Right, let's say, yeah, only holds one value or only contains one value. Yeah, then, right, is there anything else? Yeah, I mean, I think that should be okay. Because I mean, hopefully we'll get sort of 1 mark for the example, and then yeah, sort of, I guess 1 mark for it doesn't have to be defined in terms of other data types. And then yeah, maybe saying atomic, right? That might be another mark. So I mean, here, well, I mean, obviously many examples. Let's just go integer. Right, of course you could go real. I mean, you could go yeah, char, right? You could go Boolean. I mean, something like a string, like I would kind of be wary about saying a string. And the reason for that is, technically, I mean, strings are usually just implemented as, well, let's say arrays of characters. Right? I mean, that's how you can think of a string. That's why most programming languages will allow you to do, let's say, like ABC, right? And then they'll allow you to, let's say, the array, the array brackets, and then something like 1. Now, of course, I mean, well, let's say in pseudocode, right? Obviously, character 1 would be A. Most programming languages, of course, is going to start at index 0. So yeah, you do, let's say index 0, which would of course get character A. And of course, well, the reason this notation works is again because, well, strings are literally just, arrays of characters. Yeah, that's why I'd be kind of wary of saying strings for this. Just think of something simple like an integer, a real, right, a Boolean. Right, then we want to write pseudocode statements to declare the set type even numbers to hold the set of even numbers between 2 and 12. Right, so I mean, yeah, I guess, well, this one, either you know the syntax for a set, yeah, or you don't. And yeah, I think this is a bit difficult because actually a set is new on the syllabus. Maybe just in the past 2 years, I think. Right, so, well, the way we do that then, let's just go type. Right, then we say, and like to me it's a bit strange because we actually need 2 statements. One, I mean, like, I don't know, maybe let's call it integer set. So here, like, this is kind of like the type of set, right? Then, well, then we go equals, and we just go set of, and then here, well, it's going to be a set of what integer. Yeah, I don't know. Like, to me, honestly, this syntax is a bit strange. Right, then the next one, well, then we just go define. So I guess what it says, right, even numbers. So here, then we have the identifier, right, even numbers. Right, then we have brackets containing all of the values. So, well, 2, yeah, what, 2, 4, 6, 8, 10, and 12. And then, alright, so I've kind of gone over space, but of course, well, then, like with any sort of declaration, we just need the colons. Right, I'm just going to do an arrow here, although, of course, I think in the exam you can fit all this on one line. Right, and then this is going to be the integer set. So, just to recap, I mean, first, then we have to create this sort of custom type, which basically, well, I mean, here let's call it an integer set. And we're going to say, right, that's going to be a set of integers. Right, then we actually define the specific instance of the set. So it's almost like a class where, this is almost like the template, right, the class. Whereas, yeah, this even numbers, well, this is kind of the specific instance, right, of, let's say, an integer set. And of course, yeah, these are going to be the values. We say, yeah, this is kind of, well, let's say the set type, basically. Okay, then for Sheila has a customer called Fred. Right, Fred wants to send Sheila a confidential document as part of a transaction. Explain how Fred uses asymmetric encryption to send his documents securely. Alright, so I'm just going to do a diagram here. So, well, let's say Fred, yeah, Sheila. So, of course, well, Sheila is going to have, well, let's say a public and private. Likewise, Fred, I mean, he's also going to have a public and private. Now, if we're talking about sending documents, and, well, of course, right, Fred is the one sending, right, therefore, what Fred is going to do, well, he's going to take his document, he's going to encrypt it, let's say the plus, and well, I mean, to do that, he's going to use Sheila's public key. So I'm just going to say like spub, and we can say, I know this is the document, right? So the document, you obviously were encrypted with Sheila's public key, and then obviously in order for Sheila to decrypt it, right, she's then going to use her private key. Now, if we're talking about signing documents, yeah, obviously, well, digital signatures, then right, digital signatures, well, Fred would, let's say, yeah, I mean, okay, right, Fred would sign it with his private key. And then when Sheila wants to verify it, well, Sheila would then use Fred's public key in order to verify. Yeah, so hopefully that makes sense. Let's say, I guess we can say what, I don't know, maybe both Fred and Sheila will have public and private keys which have been generated by an algorithm. Let's say, yeah, both Fred and Sheila, let's say what will have unique. Right, unique, yeah, public and private keys. right, let's say, yeah, generated by an algorithm. And maybe in brackets, right, let's just say let's say public and private key are mathematically related. Yeah, I think, I don't know, like sometimes they give you a mark for saying they're mathematically related. Okay, and then what we can say was, so when Fred, yeah, let's say, yeah, okay, alright, so yeah, Fred is sending. Alright, so let's say, yeah, when Fred sends the, or, yeah, I mean, alright, maybe before, or yeah, as. Yeah, alright, okay, well, let's say when sending. Alright, when sending. Right, so Fred, what he's going to do, he's going to take Sheila's public key. Alright, so let's say Fred will encrypt his document. Encrypt his document. Yeah, let's say what, using Sheila's public key. I don't know, right, let's say, and transmit it over the network. Yeah, I mean, I guess here it doesn't say they're actually using the network, but I mean, I guess probably we can assume that. Or we could say, well, yeah, and send it to Sheila. Oh, that's more general. Yeah, and actually, maybe we could mention like ciphertext. So let's say, right, encrypt his. Yeah, okay. Right, so I'm probably just going to draw an arrow here. Right, so let's say, right, encrypt his, well, plaintext document. And then what, maybe in here, let's do another arrow. Right, let's say, yeah, what, into ciphertext. Yeah, using Sheila's public key. Alright, let's say, yeah, maybe here. Alright, and then what we say, yeah, and an encryption algorithm. I mean, again, you know, like, I mean, this is probably quite obvious, you know, which is why a lot of people don't write it. But at Cambridge, I mean, well, often they do give you marks, you know, just for writing the obvious as well. Right, so Sheila's public key, yeah, well, and an encryption algorithm, right, and send it to Sheila. I guess, well, yeah, when she receives it. Or, yeah, I guess, well, when she receives it. Right, Sheila will use, I mean, what, yeah, Sheila will use the same encryption algorithm. Right, the same encryption algorithm, right, and her private key. Right, yeah, and her private key, let's say in order to decrypt the document. Right, okay, yeah, in order to, right, decrypt the document. Yeah, I mean, I think that should be enough. I mean, like, since they're talking about a confidential document, and I don't know, like maybe this is some sort of, you know, business document or some legal document. I mean, you might also want to mention digital signatures. So yeah, let's just mention that. Right, let's say, yeah, in order to, I guess maybe you'd like to, or okay, let's say in order to authenticate the creator of the document, or yeah, or let's say, right, in order to prove that Fred created the document. Right, yeah, in order to prove that Fred created the document. Right, I'm going to go down right here. Well, let's say, right, yeah, he could sign it. Right, he could sign it using his private key. And I suppose if you wanted, you know, you could also mention, well, first he could hash it, right? Then he could, you know, sign the hash. But okay, all right, let's see. Yeah, he could sign it using his private key, right? And Sheila, yeah, Sheila could verify the identity by, well, I guess just verifying it using Fred's public key. Yeah, all right, let's say verify. Okay, right, verify the identity. Right, using, yes, it will, okay, let's say using Fred's public key. Yeah, and I suppose, I mean, if you wanted to talk about, let's say, proving that the document hadn't been modified, well, then you'd also mention, they could hash it as well, right? So, okay, let's say you would hash it, right? Then you would, sign the hash. And yeah, well, then you could both, prove the identity, right, and prove it hadn't been modified. Okay, right, for 5, we want to write this infix expression in reverse Polish notation. And if we say, well, RPN, right, this is also just called postfix. So postfix, of course, well, this is where, let's say, the operator comes after the, well, I guess, well, the operands. Yeah, so the operator will be after the operands. Now, the way we do this then is just creating a stack and a queue. And of course, while the stack, this is going to hold the operators, and then while the queue, well, I mean, of course, ultimately the queue is going to hold the final expression. But well, let's just go through this then. So if we see a bracket, well, okay, hang on, right? If we see a left bracket, we're just going to add that to the stack, right? Or push it to the stack. Now, if we see right, an operand, so either that can be a number, right, or it can be here, let's say like a variable. Well, then we're just going to enqueue that, right? Just add it to the queue. Right, then if we see an operator, well, I mean, okay, let's say we're going to push it to the stack. And we also want to look, right, what is the operator underneath, or yeah, what's the operator currently on top? Now, what we say is that if the, let's say if the operator underneath has a lower precedence, then we're going to continually pop operators, right, until we reach an operator with a higher precedence. So just to, well, cause I think we did this last time as well. So we think, well, the lowest precedence is going to be plus and minus, right? Then we've got what, let's say, multiply and divide. I think then, yeah, I suppose then we're going to have what, exponentiation, and then finally we're just going to have brackets, okay, which have the highest precedence. So because in this case, well, the minus is going to have a lower precedence, than the bracket, right? Therefore, we're just going to push it on top. Right, then we see 2. So, well, 2 is a number, right? So we're just going to add, add it to the queue. Right, then we see a plus. Now here, then, what the minus has a lower precedence, right? Therefore, I mean, basically, well, the minus is then going to get popped off and added to the queue. So yeah, let's just do that. Right, so that gets added to the queue, and then well, the plus, right? Well, now we see, of course, we've got a bracket at the top. So right, therefore, the plus is going to go above. Right, since again, well, the plus has a lower precedence than the bracket. Right, then we get an 8, so again, just add it to the queue. Right, then we get a right bracket. Now, when we get a right bracket, we're going to repeatedly pop everything from the stack, right, until we find a corresponding left bracket. So here then, well, this plus just gets popped and added to the queue. And then, yeah, we're just going to pop everything, right, until we see that left bracket. Right, then we get a divide, so again, right, push that to the stack. Right, then we get a left bracket, so right, this has a higher precedence. And well, okay, actually, right, brackets are always added to the stack. Yeah, you never kind of like, pop things off. Right, then we get a 9, so yeah, let's add that to the queue. Right, then a minus, again, that has a lower precedence, so push it to the stack. Right, then a 5, so we'll add it to the queue. Right, again, well, now then we've got a closing bracket. So just as we did before, well, we're going to pop everything, right, until we find that corresponding left bracket. So yeah, that's going to be minus. And well, now since we're at the end, when we get to the end, we just pop everything from the stack. And of course, yeah, just add it to the queue. Alright, so I think this here should be our final expression. Right, now we want to evaluate this RPN expression, and well, yeah, of course, right, using these values. Right, show the changing contents of the stack as the RPN expression is evaluated. Right, so first then we get A, so well, let's just push A to the stack. Right, then we get B, so well, B is going to be 3. So well, okay, right, let's write the 6, right, and then, okay, hang right, it's D, yeah, not B. Right, so well, then we're just going to write the 9 here. Right, now we see an operator, so what we do, we take the 2 top elements on the stack, we pop them, right, we sort of, let's say, perform the calculation, and then, yeah, what we're going to push the result back onto the stack. And the thing that you have to get right is you want to think, let's say the top one, so the top one is going to be popped off into the right position, and then, well, let's say the bottom one gets popped off into the left position, and then, well, here we have the operator in the middle. Now, of course, for plus it doesn't matter because, well, 6 plus 9 equals 9 plus 6, right, it's the same. But of course, if we were doing minus, right, like 9 minus 6, well, okay, let's say, yeah, I guess I'll use Pseudocode, right, I mean, that's going to be not equal to, obviously, well, 6 minus 9, yeah, same for division. So anyway, if we think, well, 6 plus 9, well, of course, that's going to be 15. In fact, yeah, I shouldn't have actually erased them, so let's put them back. So well, here then we're going to write 15 in the next box. Alright, the next stack. Right, then we get another A, so well, let's go 15, and then what A is going to be 6. Right, then we get a B, so I mean, let's just write all of these, right, 15, 6, and right, 3. Right, then we get a plus, so we're here, well, I'm just going to write the 15 again. Right, now of course we have 6 plus 3, right, so that's going to be 9. Now we see a C, right, so that's 7, so yeah, let's just write all of these, 15, right, 9, and 7. Okay, right, then we get a minus, so well, that's going to be 9 minus 7, that's going to be 2, and of course you get the 15 here as well. Right, then we just get the multiply, so what, 15 times 2, and yeah, that should be 30. Now we want to write this RPN expression in infix form, and this is similar to what we just did above, using a stack, but rather than actually just, evaluating, well, let's say evaluating each expression as we pop them off, yeah, we're just going to, combine them to actually form the, to form the actual, infix expression. Right, so again then, we see, well, let's say, operand, right, so obviously, well, a number, right, or a variable. So we're just going to push that onto the stack, right, then again we get A, right, another operand, then we get C. Right, so now then we see a minus, so what we're going to do, we're going to pop off the top two. So let me just do that, right, we're going to pop off C, we're going to pop off A. Right, then we're just going to do that calculation, so that's what A minus C. And yeah, we push this kind of sub-expression right back onto the stack. Right, then we get a plus. So, I mean, now we're just going to do the same thing. And yeah, this is why it's a little bit annoying, because, well, they don't really give us much space to write this. So, right, that was going to be what? So, B minus, then I think was A plus C. And yeah, now I'm just going to put all of this in brackets. Right, now we get a D, so yeah, let's push that to the stack. Right, then a B, let's push that to the stack. Then we get a plus, so we're just plussing what, D and B. So let's go, yeah, D plus B, again, let's have brackets. Right, then we get a multiply, so, okay. Yeah, let me just erase that. Right, of course, now that's going to be multiply. Right, I'm just going to put this one in brackets. And then we go, what, this was D plus B, I think. Right, then we get a C, so let's push that to the stack. Right, and well, then we just get the divide. So again, well, we're obviously going to pop C off the stack. Right, pop this whole thing off the stack. And let's put another set of brackets, and then just go divide by C. Right, so this should now be our final answer. Okay, then 6, the diagram shows the logic circuit, and complete the truth table for the given logic circuit, right, and show your working. So yeah, let's just zoom out so we can see. Right now, P then, so if you look, well, P is just not A. So yeah, this one's fairly simple, right, just 4 1s and then 4 0s. Right, then if we look at the next one, so Q, well, Q is just going to be not B. So again, well, obviously 0, if we not 0 becomes a 1. Obviously, yeah, not 1 becomes a 0. Right, then the next one was C. Okay, yeah, hang on, right, so R, right, R is just not C. So that's right, yeah, 1 0 1 0, 1 0 1 0. Right, then we get S. So S is going to be, okay, right, so well, S is P, right, or it's B, yeah, or it's C. Okay, so here we're obviously, well, we're looking for, yeah, P or B or C. So actually, I mean, well, we can quite easily see, well, these four. So let's just go, yeah, 1 2 3 4. Because of course, well, we can see the P here, right? That's obviously 1. Right, then if we look at B and C, so well, here there's a C in this, right? There's also a B here, and yeah, there's a B and C here. Then I guess it's only this one that's a 0. Right, then if we look at T, so right, T is going to be, well, P, right, well, and Q, and then, right, and R. Okay, so if we look at the first row, so yeah, here we've got what, 1 and 1 and 1, right, that's true. But then the next one, right, no, we've got 0, right, then, yeah, then I think, right, all of the next ones are going to be false. Then if we look at Z, right, so Z is going to be what, S, right, X or T. So of course X or, well, when they're the same, it's going to be 0. Okay, so 1 X or 1 is going to be 0. But then here, right, 1 X or 0, right, when they're different, it's going to be 1. So right, that's going to be, yeah, 1. Right, here's 0 X or 0, they're the same. And then, yeah, here they're different. Okay, so yeah, I mean, again, hopefully that's correct, as long as I've not made a, silly mistake. Right, then we want to write the Boolean expression that corresponds to the logic circuit as a sum of products. So as as we've seen a few times, these summer products, we just look at where the output is true. So of course, well, obviously, yeah, these are 6 cases, and then then we just look at the inputs, right? So A, B, and C, and we want to say, well, what value of A, B, and C, right, makes, for example, this output. And here we can see, well, it's going to be not A, right, because it's 0. Not B, right, and C. So yeah, let's just write that. That's going to be right, not A, and not B. Right then, and C. Right then, we want to OR it together because, of course, what I was saying, right, either this row is true, or this condition, right, or this condition. Obviously, this. So we're saying, well, if right any of these 6, if any of these 6 conditions are true, right, then the output is going to be true. So the next one, then we say, obviously here, right, 0. So that's going to be not A, right. Then it's B, then it's not C. So let's go, not A, right, and B, then and not C. Right, then we OR it, so this is going to be not A. Right, then this can be what, and B, and C. Right, then we get, so hang on, right, this is going to be A, this one here. Right, this is going to be what, not B. And then, right, hang on. Alright, so, well, that's just going to be C. Right, then the next one, so that's going to be what, A, and B, and not C. And then finally, well, just for A, and B, right, and C. And again, I mean, like, let's say these ones are quite easy to check because, of course, well, if we say here, alright, not A, not B, and C, so, of course, well, that's going to be, right, 0, 0, 1. So if we look, 0, 0, 1 is this one. Likewise, the next one, this should be what, 0, 1, 0. And if we look, 0, 1, 0, okay, that's there. And of course, we're looking at these outputs. So I would recommend, probably check your answer on this because I think really you can check this in like, probably 20, 30 seconds. I don't know, maybe less. Right, so then C, we want to complete the Karnaugh or Karnaugh map, K-map for this Boolean expression. Alright, so let me just zoom back in again. Maybe not that much. Right, so we've got, well, obviously, not A, not B, right, not C. So here then what we're saying, well, of course, A is going to be 0, B is 0, C is 0, right? I mean, since they're knotted. Therefore, if we're looking for 0, 0, 0, well, that's going to be, right, A is 0, right, and B is 0, and C is 0. So we're saying, well, this one is going to be true. Hang on. That one is going to be true because, of course, again, right, any of these conditions are true. And let's say, for example, Z, right? So we're saying, well, Z is true, right, if any of these, 6 conditions are true. So the next one we're looking for, what, 0, 1, 0. So again, well, 0, and then, well, 1, 0 is going to be here, so that's going to be this one. Right, the next one, so 0, 1, 1, so 0, 1, 1 is this one. Right then, alright, so hang on, so, well, right, 1, 0, 0. So 1, 0, 0 is this one. And then if we're looking here, right, so 1, 1, 0. So right, 1, 1, okay, 1, 1, 0 is this. Right then, what, ABC, right, so 1, 1, 1, right, that's going to be this. Then I guess here, let's fill in the zeros. Right, then we want to draw loops around appropriate groups in the K-map to produce an optimal sum of products. So when it says optimal, well, of course, that means, one, we want the groups to be as big as possible. However, we do have to say, there's a few rules. I mean, one, the groups have to be a power of 2. So we say, for example, we can draw, let's say we can draw a circle, square, around, let's say, like, obviously, 1, 2, 4, 8. But for example, if we have like a group of 3, of course we can't. So I don't know, well, let's say we have something like a 3 like this, right? We would actually have to make 2. So we have one, which is, those blocks, and then another one, which is going to be those blocks. Because, of course, remember, we have to make sure that the blocks are as big as possible. You wouldn't want to have something like where, let's say you do a 2 here, and then, just a 1 by itself. Because in this case, well, this won't actually be simplified. That's why we need to make the block as big as possible. Again, right, also no diagonals, right? So they can be horizontal, they can be vertical, right? No diagonals. And also we can have wraparound, which I think we're going to see here. Because, I mean, if we think about that, I mean, so here we can make a block of 4. Now, of course, like, we can't have the whole thing wrap around. Because if we wrap around the whole thing, well, we're going to get a block of 6, and 6 is not a power of 2. So right here then there's going to be 1 block, and right, maybe I'm just going to use a different color. Right, then we see the next block, so that's actually going to be these, and maybe that color doesn't show up that well. And what then it's going to be these 2 here as well. And okay, let's say the way that you can show wraparound is just by well, if we see here, right, obviously we don't kind of close this box. Yeah, if we just leave the box open, right, then that's yeah, that's kind of indicating wraparound. Of course, yeah, same on that one there. And yeah, let me just change the color to something sort of more visible. Right, then we want to write the Boolean expression from your answer to part C, well, yes, C part 2, as a simplified sum of products. So here then what we're looking for, I mean, let's start with this sort of yellow box first. Now we want to see, well, what value stays the same, what values change. Now if we look at A, well, some of these values are when A is 0, and some of the values are where A is 1, right? Because obviously, yeah, this one is where A is 0, right? This one is where A is 1, right? Therefore, because the values change, well, we just ignore that. Because what that's saying is, well, A doesn't tell us anything, sort of, about the output of this, sort of, yeah, I guess what A doesn't sort of tell us anything about the, logic expression, basically, or yeah, the output. Right, whereas if we look at B, so, well, in this case, B is going to be 0, right, but then in this case, B is going to be 1. So again, B changed, right, therefore discard it. But if we look at C, well, here C is 0, right, again, right, C is also 0. So because it's 0, well, therefore that's going to be not C. Right, then we want OR, so we just want this blue one. Again, we see, well, A is 0, A is 1, whereas A changes. But then in this case, well, B is going to be 1 in both times. So that's going to be what OR B. And then if we look at C, well, here is the 1, here is the 0. So of course, well, C changes, right, therefore we just ignore it. Now, I mean, let's imagine if C was also the same, right, then of course we would just write, what, B and C. But yeah, in this case, well, since C changes, right then, of course, yeah, we just ignore that. Okay, then 7, we want to outline what is meant by direct access as a method of file access. So I think for this, what I'll probably say is that, well, we can hash the key in order to find the memory address of the record in the file. And also, I mean, that's going to give us what, constant time, right? So rather than requiring, let's say, like linear search right through the file, yeah, or well, yeah, I guess linear search, yeah, we can just, well, directly find the location. So yeah, let's say maybe what, by, or yeah, okay, let's say what, by, right, by using the okay, well, let's say by calculating, right, by calculating right, the location of the record, right, so by calculating the location of the record, right, by hashing the key, yeah, let's say, right, by hashing the key that we are trying to find. And actually, I mean, rather than saying location, well, let's say memory location, right, just be a little bit more specific. Right, by hashing the key that we are trying to find, we can say, well, yeah, this gives us a constant, or yeah, O of 1, yeah, access time. Yeah, so I think let's say that, right, this gives us a constant, and let's put in brackets, right, that just seems, well, sort of big O notation, that's going to be O of 1. Yeah, O of 1 access time. Yeah, and I think, I mean, let's just try and be a little bit more kind of explicit. So what we can say, yeah, we don't have to traverse the file. We can just directly find the position and go to that position. Yeah, or let's say, yeah, maybe, right, we can directly seek to the correct position in the file. Yeah, okay, right, we can directly seek to the correct position, or yeah, maybe the position of the record in the file. Okay, then we want to explain how direct access is used to locate a specific record in sequential files and random files. Okay, so yeah, I think they say that for sequential files, well, that there's going to be another index file. Because I suppose for this, they're saying what the records can be of different sizes, I think. Whereas, yeah, like when they're talking about random, I think they're talking about fixed size records. So in sequential files, what you have is, well, not only will you have, let's say, the actual, record file itself, but you'll also have an index file. Then we want to explain how direct access is used to locate a specific record in sequential files and random files. Okay, so obviously if we think they're sequential files, what the records have to be stored, let's say, ordered according to some, well, yeah, obviously to some key. So maybe you have, I don't know, some like customer ID, and like maybe you have record 1, right, then record 4, let's say record 7, all right, maybe 8, yeah, 10. Now, I mean, what you'd have is, well, somewhere you'd have to store an index, right, of these. Okay, well, let's say you'd have to store an index that's mapping, let's say, the record number, right, to the actual location of this, in the file. So, I mean, since this is record 1, well, let's say this is probably, byte 0. I mean, record 4, I don't know, maybe that's a byte 200. Obviously here, I mean, the records could be different sizes, right? Maybe this one's going to be, byte 800. That one could be, I don't know, 1400, right, whatever. So, I mean, what you're going to need is you're going to need some index. Now, if it's just a simple index, I mean, I guess you say, well, I mean, it could literally just be an array, right? It could be a simple table. If you wanted it to be sort of a bit, faster, then I suppose you could store this as, let's say, like a binary tree. And then, of course, well, even if you had, sort of like millions of records in this file, well, because a binary tree is going to be an O log n search time, or an O log n access time, right, then that's still going to give you actual, good performance. So, let's try and say that maybe, let's say an index file. Right, an index file is created. And I don't know, I mean, we could say, what could be array or binary tree. Right, index file is created, and we could say what mapping, and what it's going to map the, let's say the record key value. Let's say record key value. Right, to the, I guess, what the sort of memory location. Alright, so to the memory location. Right, that the record is in the file. So I think that should be okay, hopefully. Right, then if we look at the next one, well, random files. And, like, I don't know, I mean, I think in some ways this is easier because, well, what you can say, well, it's just going to take the key, it's going to hash the key. Not actually, well, this is kind of what we said here, really. It's going to take the key, hash the key, and then just, directly find the memory location. Obviously, well, based on the hash value. Now, I mean, this is really only going to work, right, if they're fixed size. If they're different size records, well, then again, you'd actually need another index file. But yeah, I mean, if they're... if they are fixed size, then it will work. But if they're not fixed size, well, then you'll need another index file like this. Let's say they're a hashing algorithm. Let's say what will take. Let's say what will take the key. Let's say what the key of the record as a parameter. As a parameter. And let's say what and return the let's say return the starting address of that record in the file. Let's say maybe starting memory location or memory address. Okay, I mean, let's just say it's return its starting memory address in the file. Because I think otherwise it's gonna we're gonna need to write a lot more. I think that's fine. I mean, like maybe you could talk about what happens if two values hash to the same value, and of course you can also maybe mention what it's gonna. I guess one. Okay. I mean, if we're using pseudocode, what it's going to be mod. If we're using sort of many programming languages, I guess what they use the percentages modulus. So something like 5 mod 2. And I think what usually they're going to choose a prime number, something like 11. Although probably bigger than 11 to be honest. I mean, all right, maybe let's make that so we could say, maybe what modulus by a prime. Let's say modulus by a prime is used to reduce collisions. And then what we can say, if there is a collision. I mean, all right, let's say if there is a collision, then there's going to be 3 methods. So one is going to be linear probing, And that's basically where if there's a collision where you just search in the next, let's say, search in the next position, right, search in the next element. Right, the other one is going to be the overflow area. So you have a completely, sort of separate part of memory, which is going to be an overflow area, where you just kind of like serially append, each collision to that. So of course, let's say the first collision will just, go in the first sort of overflow box. The second collision obviously goes, in the second overflow box. And then the third one is going to be chaining, where rather than actually storing, so actually I suppose with a file you can actually use chaining. So let's say linear probing and let's say like an overflow collision area. So if there is a collision, we'll say then, then linear probing, or maybe a separate overflow area could be used. I think that's okay. Right, then 8 says complete the pseudocode to find an item in a 1D array widgets of type string using linear search. Right, so widgets has 50,000 strings. Top of list. So I think like in paper 31, I guess top of list just means the start of the list, right, the first element. Of course, end of list, right, the count. Then to find what we're trying to find. Of course, then we've got found, not in list. Right here, then they're just going to initialize the start of list, right, top of list, and end of list. They're going to output. Then they input the item they want to find. Now this is again, I mean, like if you, I suppose if you've seen the video on, of course, paper 31, then this question is actually quite similar. Of course, in the exam, I guess you wouldn't have the luxury of seeing both papers. So let's say here then, this is going to be the same, where it's just going to be found. And we just want to assign false to found, because the while condition, I mean we're going to continue looping, right, while found is equal to false. Then also while not in list is also equal to false. And I think not in list, this is basically just a variable, checking for if they've searched all the elements. So of course, I mean, you could also do if count is, let's say less than or equal to 50,000, right? Then you would probably want to continue. I think, I mean, that's what they're using this not in list for, I think. Right, okay, so then something, and they're going to assign found true. So I guess what we want to go widgets. Let's go widgets, and then what is the current index? So I guess this count then is going to be the index. Let's go count, and what we want to check if that's equal to find. Then if it is, set found to true. Right, and so actually, this part is weird because normally you just have this in an else. So rather than if, you just have an else. But because they don't have an else, then we also have to check if found is not equal to false. If found equals false. Because otherwise what you might have is, let's say if it finds it in the last element, then we're going to say found is true, right? Because it is found in, element 50,000. But we wouldn't want to do this where we check the if. If we're incrementing by 1, I guess we would check, if count is greater than 50,000. So for example, if we just did this, you could have a situation where, if we find it in element 50,000, right, then we're going to assign true to found, right, then we're going to increment count by 1. So of course, now count is going to be, 50,001. So in this case, 50,001, right, would be bigger than 50,000. Then we're going to set not in list to true. So, I mean, here we've kind of got conflicting, let's say conflicting results, right? Because of course, we're saying found is true, but then we're also saying not in list is we're also saying not in list is true. And really, I mean, I don't know, to me this is weird where they've got a found and they've got a not in list. I mean, honestly, they could just completely delete this. I'm not sure why they've done it. you know, I guess sometimes they sort of deliberately give you like bad code and then they say, well, you know, how could this be improved? But yeah, I think if we go here, right, they actually don't ask us to do that. Anyway, so what we want to do, we want to say, well, count is greater than 50,000, and then we'll also and this should be, well, let's go found equal false. Yeah, I mean, again, just to prevent having this situation where we say, well, found is true, right, and not in list is also true. And then, all right, so yeah, here then there's nothing else, and of course we just check if found equals true. Yeah, then it's just going to output the position. Okay, then we want to compare the methods used by the linear search and binary search algorithms to find an item in an array. Refer to big O notation in your answer. Okay, so I suppose one thing we could mention, of course, one is going to be the speed. Right, linear, what's that's going to be? Well, just, yeah, hang on, that's going to be O of n. Of course, binary search, that's going to be what, O log n, or we could say, yeah, log base 2 of n. We could also mention that binary search has to be sorted, whereas, of course, linear search, well, this has the advantage of working on an unsorted list. Yeah, and I suppose what you can sort of mention how they work, so linear search will just search each element one by one, whereas binary search, it will obviously will have the, let's say, start pointer, end pointer, right, get the middle element. Yeah, if it's bigger than the middle element, of course, it will then just, you know, search the right half. If it's smaller, it will search the left half. Yeah, so I think, I mean, probably that would be about 6 marks if we explained all of that. So yeah, let's just try and do it. So, I mean, I know, okay, let's just, yeah, let's probably just talk about linear search first. Right, linear search, right, let's see, yeah, is an, well, that's going to be on, yeah, algorithm. Or yeah, maybe okay, rather than saying on, let's say has, right, linear search has, alright, maybe has an, yeah, on time complexity. And let's explain that. Alright, so let's say since, yeah, what maybe each element is, yeah, maybe each element, right, is searched one by one. Right, until we find the element or we reach the end of the list. Yeah, right, so until we find the element, yeah, or reach the end of the list. And we could say what the array, yeah, I mean, I don't know, let's say what the array doesn't have to be sorted. Yeah, okay. Right, and then, well, let's say, right, in contrast. And I think, right, I'm going to use the same format. So, I mean, first then let's talk about the time complexity. Right, in contrast, binary search, yeah, has, right, let's say has an, well, O, right, well, log base 2n. Right, yeah, time complexity. I mean, well, I mean, basically, I'm going to copy this sort of word for word, you know, where appropriate. Right, let's say, well, since, what we can say that the array will be split in two, and if the element is sort of bigger than, yeah, okay, let's say that. Right, yeah, since the array will be split, yeah, okay, right, since the array will be split in two, right, and we say, right, and, yeah, and if the, yeah, if the target element is bigger than the midpoint, and I suppose, I mean, rather than just saying, well, the array will be split in two, let's maybe say repeatedly. Yeah, okay, I mean, let's say that. Because obviously, I mean, it's going to be each stage, right, it's going to be split in two. Right, repeatedly split in two, and if the target element is bigger than, yeah, right, is bigger than the midpoint. Yeah, we will search the right half. Yeah, let's say, yeah, the right, yeah, I know, like, let's say the right subarray, or, yeah, the right half. Well, let's say if smaller, let's say, well, if smaller, search the left half. Yeah, of course you could mention, well, if it's found, of course we just stop. Or maybe let's say, yeah, and if found, we stop. And then let's also mention, so we said, well, linear search has to be sorted. Okay, linear search doesn't have to be sorted. But let's say, right, however, or yeah, I know, yeah, maybe a drawback. Right, let's say binary search only works on sorted arrays. Then we want to outline two benefits and two limitations of a virtual machine. So I think benefit one, probably testing. You know, we can test our software on a large number of different operating systems and also, you know, different virtualized hardware. So for example, maybe you'd want to test on a, I don't know, let's say a 4 GB machine. Obviously, well, in terms of RAM, you know, you might also want to test on a, say, 32 GB RAM machine. And of course, well, obviously, yeah, with a virtual environment, right, with a virtual machine, then you can do this. So yeah, let's say testing. Well, yeah, can test right on a large number right of different OSs. Yeah, let's say right different. All right, let's say operating systems. Right, operating systems. Yeah, well, and let's say right, yeah, and virtualized hardware configurations. So again, you know, for example, different amounts of RAM, you know, different number of cores. Right, yeah, virtualized hardware configurations. Well, let's say, yeah, quickly and cheaply, or yeah, maybe easily and cheaply. Yeah, I think probably easily is a better word, right, rather than quickly. Right, yeah, easily and cheaply. Unless it, well, let's just put in brackets, right, yeah, since we don't have to buy the physical hardware. Right, yeah, since we don't, right, have to buy, yeah, okay, right, buy the physical hardware. Right, let's say HW. Of course, you know, in the exam, right, hardware. Right, then, benefit two, I think you can probably say security. And there was a, well, yeah, okay, I mean, there was a video I was watching which was talking about this. Now, they were saying, let's say, for example, a web host, so, well, okay, you know, just a web server, like, they wouldn't want to have it where, you know, all of their customers are all just running on one server. Because you might have a situation where, let's say, you know, one website has a vulnerability, right, they get hacked, someone manages to, you know, obviously install malware onto their system. Well, now, of course, right, potentially all the other websites running on that same server, you know, also going to be, yeah, also going to be infected. You know, they're going to have their data stolen, right there, you know, files corrupted. Whereas if you have like each customer on their own virtual machine, well, then if one customer gets infected, right, that's not going to affect the other customers, because, well, yeah, obviously all of those virtual machines are in their own kind of, you know, distinct environment. Yeah, okay, I mean, they've got their own, you know, memory space. Yeah, things like this. I mean, but like, I mean, okay, so, well, not only is it for, let's say, you know, different customers, but it can also be right on your own device. Let's say you have some file which you're, you know, unsure about. Well, rather than just, you know, sort of letting it loose on your own system, right? Because, yeah, I suppose what, I mean, maybe it's going to appear legitimate, but, you know, of course, it could be a Trojan, right? Trojan horse or something. Instead, of course, you can test that inside a virtual machine. And again, anything bad that happens in the virtual machine, well, that's not going to spread to the host operating system. So yeah, let's try and say that right. We'll say security. Let's say well, maybe programs, or yeah, we could say what executables can be tested. Right, let's say yeah, executables can be tested. Right, let's say yeah, and users right can run right in their own VM. And I suppose, well, all right, I mean, rather than saying VM, right, let's say virtual machine. Yeah, and well, let's say like e.g. like web servers or web hosts. We can say what anything bad, or yeah, or let's say yeah, any malware. Right, let's say any malware, right, slash corruption. Let's say on one, or yeah, maybe right in one VM. And we'll say what can't spread to the other VMs. So yeah, I mean, it's kind of like having a quarantine zone where you're just isolating it. All right, well, let's say yeah, other VMs, right? Yeah, or the host system. Yeah, let's say right, the host OS. Right, then some limitations. I suppose, well, the main one's just going to be performance. So let's say the performance will be, right, okay, the performance, what will be worse. Yeah, than, what, let's say, than the, I guess, what, the host OS. Yeah, I think I'm going to say OS, that's fine. Of course, you could say operating system. Right, the host OS, yeah, on the native hardware. And I suppose if we want to explain that, what we can say due to, I guess we can say what, let's say the overheads of, you know, sort of, well, function calls, you know, additional communication. So yeah, let's say overheads. And we can say what, like additional communication / function calls. Because of course, I mean, all right, yeah, fine, it's a virtual machine. But of course, you know, that has to go all the way down the stack, right, eventually down to, well, obviously, well, the native hardware. Which, yeah, I think we'll see in a minute, right, the next question. Right, so additional communication, right, / yeah, function calls. Right, then limitation 2. I think for this one, we can probably say that some software, in particularly low-level software, for example, drivers, yeah, sometimes this can't be installed on a virtual machine. And I know, for example, well, me, right, I had a situation where I wanted to install some like AI, yeah, some AI library right on a virtual machine, and I had a problem where I think, for example, that graphics card, I mean, yeah, that wasn't supported inside a virtual machine because, of course, well, that yeah, that needed okay, well, not graphics card, sorry, that graphics driver. Since, of course, well, that graphics driver, I guess, couldn't directly communicate with the graphics card, you know, through the virtual machine. So yeah, I think let's say that, right, maybe some software. We could say, yeah, in particular, like low-level software. Right, in particular, yeah, low-level software. Right, let's say like drivers. Let's say what, yeah, might not be supported. Right, yeah, might not be supported. Or let's say, yeah, all right, okay, let's not say supported. Let's say, right, might not run, or yeah, might not work properly. Right, yeah, might not work properly inside the VM. Okay, right, so yeah, this is the next one I was talking about. Explain the roles of the host operating system and the guest operating system as used in a computer system running a virtual machine. So, I mean, like I was saying here then, I mean, let's just draw it again. We're going to have, of course, well, the hardware is going to be at the bottom, and I suppose you can say, well, this is the host hardware, or the, yeah, sort of native hardware. Right, then on top of that, well, then you're going to have the host OS. Right, on top of the OS, I mean, I think you can call it a hypervisor. I think in the book they call it what? Hang on, right, the VM implementation software. Yeah, so right, implementation software. Right, then on top of that, so I mean, you can think like I don't know, like if people are familiar with this, something like VirtualBox. Yeah, there's also what VMware. I mean, VMware is also, you know, popular software, and of course, well, you can just download, right, either VMware or, well, VirtualBox is the one I use. And then yeah, of course, well, with this, you know, you can then install a different operating system, right, on your own computer. Right, so on top of the hypervisor, well, here then, I mean, let's say what the VM, yeah, let's say what the VM kind of emulated hardware. Yeah, and this is going to be what's the sort of virtual machine 1. Of course, well, let's say here we have, you know, sort of the VM2. Right, yeah, VM2. And again, well, of course, that's going to be the sort of emulated hardware for the virtual machine 2. Right, then on top of that, well, this is there where you're going to have, well, let's see, the VM1 OS. So maybe this is, for example, Linux, right? Maybe like Ubuntu or something. Right, then, of course, well, let's say here we have, well, VM2, right? Well, VM2 OS. Yeah, maybe that's Mac, for example. And then I guess on top of that, well, then you're going to have, let's say, well, I don't know, let's say the VM applications, or, I mean, well, basically whatever applications you're running inside the VM. Of course, you know, this could be a web browser, I mean, it could be a game, it could be some, yeah, like VS Code, right, development software. Yeah, maybe it's a database. So, of course, I mean, I don't know, well, let's say you've got some database, for example. Of course, database, well, that's going to have to do lots of, like, reading and writing, right, to the disk, right, from the disk. So, of course, any read or write request that you make, right, first it's got to go to the virtual machine operating system, right, then that has to go to the emulated hardware. Of course, right, then it goes to, well, let's say the hypervisor, you know, like VMware, VirtualBox, right, just the software. Right, then, of course, that goes to the host OS, right, then it goes to, well, obviously, yeah, the native hardware. So, you know, of course, well, this is why it's going to be slower, right, so, well, there's obviously all these additional layers. So, yeah, I mean, let's try and just kind of explain that, and I'm just going to erase some of this just to give myself more space. Right, so we say what the host operating system, I mean, of course, well, this is going to, yeah, I guess we can say what it's going to directly communicate with the hardware. Yeah, okay, right, so let's say the host OS, right, can directly communicate, right, yeah, directly communicate, right, with the, what, native hardware. Right, let's say what a hypervisor. Yeah, let's say hypervisor, right, slash, well, sort of VM software, or yeah, VM implementation software, right, can be installed on top of this. And what we can say, what it's going to kind of like maybe allocate. So yeah, we can say what it's going to allocate some of the native. Yeah, let's say it's going to allocate some of the native resources to the virtual machine. And of course, when we say resources, well, we mean CPU, RAM, yeah, things like that. Right, okay, yeah, let's say we're and allocate. Right, some of the native. Yeah, the native, let's say what hardware resources. Okay, right, resources. Yeah, let's say what to each VM, because of course, you know, you could have like multiple virtual machines. Right, yeah, to each virtual machine. Right, so what else does it want? So yeah, explain the host, the guest operating system. Right, okay, so we say what the, well, of course, right, the guest operating system will run on top of this emulated hardware. Yeah, right, let's see, well, the guest operating systems, because of course there can be many. Yeah, the guest operating systems, right, will run on top of this emulated hardware. And then I think well, let's kind of mention this with all the arrows, right? So we can say what any, yeah, I guess what any sort of requests or any, I suppose what we say, kind of any like access to the resources. Yeah, I mean any access to, well, I guess hardware or yeah, native hardware. Right, will have to travel, I guess we'll have to travel down the entire stack. Yeah, I guess what entire stack or maybe entire chain. Yeah, I think stack is okay. Yeah, and I think hopefully that should be enough for 3 marks. Yeah, so I think that should be okay. And I suppose, you know, again, you could mention something like, of course, what each, let's say each, yeah, okay, right, so each guest operating system is going to be, you know, sort of like uniquely isolated from each other one. Of course, it's going to have its own memory space, right? It's going to be allocated its own CPU cores, yeah, etc. Yeah, of course, well, it's going to have its own, you know, virtual hard drive as well. Then 10, a declarative programming language is used to allow clients to choose daily activities at the beach. Right, so we've got what the activities that are paddleboarding, sailing, right, etc. Clients, I guess, yeah, the people. Right, then we've got choice, so I guess what Petra chooses rowing. And then right, done, so what Henry has done jet skiing. And then yeah, if we just look at the descriptions, right, these clauses have the meanings. Right, so yeah, 1, paddleboarding is an activity. Yeah, so clause 1, right, paddleboarding is an activity. Yeah, that makes sense. Right, 6, Steve is a client. Okay. Yeah, Petra has chosen rowing. Yeah, okay. And Henry has already done jet skiing. Yeah, which we see here. Right, it says Jane is a client who would like to choose the activity surfing, and she has already done sailing. So let's see then. I mean, well, yeah, does Jane exist? So if we look at the clients, we've got what, Antonio, Henry, right? Maybe Eliza. Yeah, okay. So I think here then there's no Jane. So let's go client, and then okay. All right. So yeah, I guess right here's where you've got to be careful. Now, if we look at these, of course, well, they're all small letters, and the reason they're small letters is because, well, in, for example, Prolog, anything with a big letter is going to be a variable. So yeah, therefore we also want to go Jane, right, with a lowercase j. Yeah, just to make that, well, let's say like an atom, right, a fact, yeah, rather than a variable. Right, then the next one, right, so let's try activity surfing. I mean, so does surfing exist as an activity? All right, no. So yeah, let's just go activity surfing. Right, then I think the last two should be okay. So, right, so yeah, what has she done? Alright, okay, so well, she would like to choose surfing. So that's going to be what, choice? Yeah, choice Jane surfing. Right, and then, right, so done. And that's going to be what, done, that'll be Jane. And, right, sailing. Yeah, and actually, right, I will make sure just to have the dot here as well. So yeah, I guess we should end all of these with the dots. Right, it says using the variable lists, right, the goal, well, alright, choice, list, and rowing is going to return, well, basically just a list of all the people that do rowing. Right, so what's the result returned by the goal? Well, choice, list, sailing. Right, I mean, so who has done sailing? Or yeah, well, who wants to do sailing? So I guess what, Frankie, Eric. And then if we see here, right, so well, yeah, Jane, she's choosing to do surfing. Right, but yeah, I guess, well, not sailing. Yeah, since she's already done that. Alright, so, yeah, wait, was this, well, I forgot, wait, it was Eric and who? Okay, Frankie. And yeah, I mean, let's get these in the correct order. So, I mean, yeah, Frankie was the first one. Alright, then let's have the comma, and then we'll go Eric. Right, it says C is a client who would like to choose A if A is an activity and C has not already done A. Okay. So, I mean, I will be honest, actually, this one I did check the answer because it was a little bit strange. So, like, I was thinking, well, I mean, like, kind of here, I mean, it tells us that C is a client, so I thought we could just assume that. But they actually want us to also check that. So, they want to go, well, client. Hang on, right, they go client, yeah, then we go C. Right, then we can use the comma for and. And I mean, if you haven't actually had any practice with Prolog, then I think, well, this is the one they recommend in the book. Yeah, some software called SWI Prolog. Yeah, I mean, this is the one we also use, right? So I'd recommend, downloading this. Yeah, kind of having a play around with it. Right, so well, we say client C, right, and so what is going to be A is an activity. So let's go activity A. Because I mean, what this is doing is, well, it's basically saying, well, yeah, obviously is C a client, right? I mean, this is just going to return true or false. So, and if there is a client, with say whatever, well, let's say argument that this is, right? Of course, well, then it's going to return true, right? If there isn't, it's just going to return, well, I guess like false or yeah, null or something like that. Right then, I guess is there one more? Yes, so right, and C has not done A. So if it's not, well, then well, hang on, right? Let's just go not. Yeah, okay. And I think, yeah, this should... Okay, yeah, so actually, right, this one doesn't have to be capital letters. But I think I'm just going to do it in capitals anyway. Right, and then it's going to be done. And this is going to be... I think it goes, what, C, and then it goes A. Because, yeah, it was going to be, what, the person, right, the client, then the activity. Yeah, that was the order they had it in. Right, then the last one, we want to explain what is meant by reinforcement reinforcement learning in relation to artificial intelligence. So reinforcement learning, well, it's obviously I mean, it's going to be about what rewards and punishment, right? Feedback. So you could say what the model or the agent. I mean, basically, it's going to start just by making, you know, random choices about its environment. I guess, yeah, it's going to be making random choices. And then, obviously, if that choice is successful, well, then it'll be, well, let's say, sort of, you know, I guess what, rewarded. And basically, rewarded, I mean, that means, I guess in many situations, you know, like maybe nothing will happen if it's rewarded. Because, of course, well, I mean, yeah, you've achieved the desired result anyway. However, I mean, if, well, let's say they're, you know, punished, then what that means is, well, you're just going to change some of the weightings, sort of, you know, inside the, I guess we're inside the model. And again, that can be done sort of using back propagation. So let's say, maybe what a method, let's just say works, right? Because otherwise the method is going to be too long. Works using, well, rewards and punishments, and I think you can also call this feedback. Rewards and punishments. And we can say what, based on the agent's choices. Let's say based on the outcome, right, of the agent's choices. Let's say, and the effect it has on its environment. Just trying to like think of all the keywords they usually use. The effect it has, right, on its environment. I guess, well, let's just talk about punishments, right? So for example, if maybe if the result is unsuccessful, maybe if the choice has a negative effect on the environment. Let's say that, right? If the choice, has a negative effect on the environment. A negative effect. Negative effects, right, on the environment. What we can say, let's say the weightings, we could say what back propagation will be used. Back propagation, right, will be used. Let's say to adjust the weightings. We can say what adjust the maybe edge weightings. Let's say what inside the model. What to hopefully improve, you know, future performance, or future accuracy. Let's say, right, to hopefully, improve, and let's say, right, future, future performance, or maybe accuracy, right, future accuracy, of the model. Alright guys, so again, I think that probably went on quite long, but as always, hopefully this video is useful. Any questions, well, just ask in the comments, and see you again in the next video.